Let us discuss one more important problem, that is problem based on EMF. Myself Dr. Viresh Kalkuri, welcome to Photon Educare. So the problem is very simple. So it is in EMI chapter, electromagnetic induction chapter. So we have one conducting circular loop which is placed in a uniform magnetic field 0.20 Tesla with its plane perpendicular to the field. Somehow the radius of the loop starts shrinking at a constant rate of 1 millimeter per second. Find the induced EMF in the loop at an instant when the radius is 2 centimeter. So first we have a magnetic field. So B is the magnetic field and its value is given here. So let us write first what is given. The magnetic field, magnitude of magnetic field is given 0.20 Tesla. So we can write this as, in terms of power, 2 into 10 power minus 2 Tesla. Okay. So in this magnetic field, which plane is pointing like this, magnetic field is with the plane perpendicular to the field. So this is the plane of the loop in which magnetic field is going through this. Plane is towards you and magnetic field is like this. Once the loop is placed over a magnetic field, what will happen? Let's say its radius be r. So it is going to shrink. When it is shrinking, its size decreases, So that shrinking at a rate of dr by dt we can take. Shrinking at a rate of 1.0 millimeter per second. That means 1 into 10 power minus 3 meter per second we can take. So when it is shrinking at a rate of 1 millimeter per second means dr by dt gives your velocity. Dr by dt is nothing but it is reducing with a velocity of, or you can say its size is reducing with a velocity of 10 power minus 3 millimeter, or you can say when we are writing in a millimeter, milli means 10 power minus 3 meter per second. Okay. Then they are asking when it starts shrinking, so ultimately it will reach us a radius r. So the final radius is r is equal to 2 centimeter. At this 2 centimeter, after shrinking, its radius, new radius becomes 2 centimeter. At 2 centimeter, what is the EMF induced in the coil, or you can say circular loop? An EMF is induced only whenever magnetic field lines were passing through the surface. Suppose if you are taking one surface here, if the magnetic field lines were continuously passing on this surface, what will happen? An EMF is created. Okay. An EMF is generated. Now, what happens here? First of all, we'll take a flux phi is equal to BA cos theta. Of course, theta is maximum, that is 0, and cos 0 it is 1. Then we can take phi is equal to BA. Okay. Now what I will do? I will take differentiation of this, change of its value. So you can write B, area of the circular loop is pi r square. Then we can take this as d phi by dt, rate of change of flux. Then d by dt, you can take b outside the differentiation because it is constant. B and pi I will take outside the integration. B pi, then we are differentiating this r square. Okay. Then b into pi as it is. Then differentiation of this r square is 2r. With respect to r, we can write dr by dt. Okay. So next, b value is 2 into 10 power minus, we have written 2 into 10 power minus 2, and then pi you keep as it is, then 2 as it is, then r value is 2 into 10 power minus 2, dr by dt means it is 1 into 10 power minus 3. So now what will happen? d phi by dt is nothing but rate of change of magnetic flux gives an EMF. Rate of change of magnetic flux gives an EMF. E is equal to Then you multiply this 2 to the 4, 4 to the 8. So 8 pi into 10 power minus 7. So if you substitute this 8 into 3.14 into 10 power minus 7, then upon multiplication you are getting 25.12 into 10 power minus 7 volt. So we can also write this in terms of microvolt. How? If you shift the decimal point here, we can write this EMF E is equal to 2.5 into 10 power minus 6, or else we can write 2.5 microvolt. This is your final answer, microvolt. I hope you understood this.